Alrighty. Hello everyone. Welcome to Unit 2 of ANSYS. So now that you've completed your beam analysis and you've optimized everything and you understand what beam elements are and how it all works, we're going to move on to solid elements. So the first thing we need to do, and I'll show you how to do this from scratch, is get the axial forces in your beam elements from this thing, from this model. So easily enough, we just go beam results, axial force, put it in, right click, evaluate all results, let it do its thing. Here we go. Alright, cool. Now you can see what all your forces are, and the ones we want are that one, and that one, I suppose. Oh, look, it's 0. How good. So, take down those numbers. I won't because I can't be bothered. And that one's in negative, so that's in compression, and that one's in tension. Is that right? It's been a long time since second year. Maybe that one's in compression, that one's in tension. Yeah, that makes more sense. That one's in compression, that one's in tension. Cool. All right. Now that we know that, we're going to go over to a solid modeling software, and we're going to create the thing that holds on the rear wheel. It's called a rear dropout, and I'll show you one right now. So we're going to model that thing, right? The one that holds the wheel on, and the one on the right. So the easiest geometry to model is probably going to be a track dropout, like this one, right? Something like that. But we're just going to make it in Inventor, and then we'll put our forces on, and away we go. So let's fire up Inventor. You can use whatever solid modeling software you prefer. Please. You can use whatever solid modeling software you like. It's just I'll use Inventor because that's what I've been told to use. I am not in the correct thing. Autodesk Inventor English. That's the one. Don't use Inventor View. Inventor View will be annoying. I'll unpause you when it's ready. Rightio, so it'll come up with something like this. Use network license. I'll unpause you again when it's actually ready. Alright, so we're here. And it should come up with a new project screen thing pretty quickly. Obviously, all the software we use here is extremely fast and responsive at all times, especially when you're doing those optimizations. Alright, start working. Yep, click on this little cog thing wherever it comes up, change it to millimeters and ISO. Yeah, overwrite. Cool. Alright, and I think that one's a new part? Yeah, new part. Alright, now, I'm going to save you guys a little bit of effort when we're making this part, because we need to think about the most efficient way to model our dropout. Now, in finite element modeling, we use this thing called symmetry. Everyone knows what symmetry is, but it's important to us because it means that if something has radial or axial or planar symmetry, it allows us to cut it in half or cut it into slices and reduce the amount of stuff that we have to actually model and get an accurate model of what we're going to do, right? So, if we look at that dropout again, so I can't kind of get it on plane, but if you're looking down the axis of the bike, I could cut this thing in half, right? I could cut this thing in half, top to bottom, in the direction of this, like in the plane that these two members share, and then I get the same thing on either side, right? Neglecting like these couple of bolts, but it's pretty much the same. Right, so that's what we're going to do. We're going to reduce the number of nodes that we have to use by cutting the thing in half, and that'll make our analysis more efficient and faster and more accurate because we have a set number of nodes that we can use with the student edition. So it's all really good. I'm trying to find a better analogy. Anyway, let's go ahead and do it. So, we're just going to do an extrude, 2D sketch, and I'll do it on XY plane. Now I'm going to do this super quick and dirty, You guys hopefully can do it a little bit better than how I'm going to do it, but very quickly, just get a circle, put a rectangle on it, like so. Zoom out. You're about to see what I'm going to do is use a offset tool. It's important to remove everything you don't want to offset before you offset. I'll make that about 10 mil. Alright, cool. Do my lines. Inventor's good because you can pretty much do the whole thing freehand and it'll be great. It's not good because its zooming is disgusting. And on this remote desktop, oh my god, please! Alright. I'm just going to make something that's vaguely reminiscent of what we wanted. Again, I expect you guys to look at the actual geometry of these things more closely than I am. I'm just making something that looks right so that I can get on with this video. Alright, so you're going to make something that's vaguely like that. You might want to put in a little sweep. Let's put in a sweep just for fun. You know? What's life if you can't put in the odd arc here and there? Ah. How good! That looks terrible. Yeah, okay, cool. That'll do. Okay, just cut out things that we don't need. See you later. Hopefully that'll work itself out. Alright. There's a sketch. Now I'll extrude it. Now, the important thing that I said earlier was that we're going to do it half the thickness of the thing, right? Now I'm going to assume that it's 10 mil thick. You can assume that it's 10 mil thick, which means we're going to make a 5 mil thick thingo. Also, I expect you to do multiple extrudes, because you should. Is that going to work? Yeah. So do multiple extrudes, like get the thickness correct around here, do a sweep around there, do some chamfering on these edges, make it all look nice. Alright. Ah, that didn't do the thing. Great. Yep. Check. Alright, cool. So now, important, export, file, export, CAD format. You're going to export it as a step file. If you don't export it as a step file, it won't work. Step. Save it in your documents or wherever. Yeah, cool. Save. Alright, and now I'll pause you and I'll open it up in ANSYS and we'll get cracking. Okay, so you're going to open up ANSYS. I've got my beam analysis open here. You just take your static structural and drag in a new one, pop it down, then you right click on your geometry, import geometry, and then I've got it here, but you can just browse and find it. Drop out half. And it should attach. Hopefully. It's very important that you use step files, otherwise ANSYS won't play nicely with Inventor files. It just never does. I don't know why. They're meant to work together, but they never did. Anyway, I've gone ahead and done something a little bit more detailed, the likes of which I was hoping you'd be able to do. So that's a nice little example, but I haven't shown you how to do it, so you have to work out how to do it yourself. Cool. Alright. Now, let's do the thing. So, we're going to apply a symmetry. Now, symmetries are important because without symmetry constraints, which hopefully Michael will teach you a bit more detail about in the lectures, symmetric, and then we're symmetric about the z-axis. Michael will teach you, hopefully, mathematically what they're all about, but pretty much it allows us to have half as many nodes, half as many elements, and allows us to get equally precise results. So, Now we'll solve that like it is. Go to my static structural, I'll apply a couple of supports, fix support, control click, yeah, that looks nice. And I'll apply my loads. Actually, a better way of doing this, I'm going to invert that. Apply a fixture there, and I'm going to delete that. So it'll be easier for you to apply the forces that you've been able to get out of your beam model as follows. So if you do apply that, and then I don't know what direction that's going in, but that's okay, I can just make it in the X direction. It'll be easier for you to apply your loads as found in your models if, is that going to be in the positive X direction? Yep. If you do it as follows. So I'm going to put a force there. So if you fix where the wheel attaches and you apply your forces here and here, it just gives you, it's just much easier. It's just heaps easier because you can put the forces here as opposed to having to work out the vector force that would make the correct amount of force go through those two members. You can just put the force there and there. Anyway, let's carry on. So I'll put a force here. Hopefully that'll work out. And I don't remember the magnitude on this one, so I'm going to just guess it was 70. Yeah, sure. Apply. Do I have a direction for that? No, I don't. Click to change. Can I reverse that? Direction. Okay, maybe I can just make that negative. Yeah, perfect. Alright, so that's, yep, into the plane. That should solve. Right, now we're going to solve it. And then we're going to do a thing called mesh refinement, which hopefully Michael's told you about in the lectures as well. But mesh refinement is when we get a more precise result by increasing the number of nodes. So another benefit of cutting this thing in half is that we actually get to kind of see what it looks like inside. It's very exciting and fun. You get a nice rainbow. We can talk about mesh quality and all that stuff. So I'm just going to take my solution and I'll get my von Mises stress and evaluate. There you go. Right, so the keen among you may have noticed that our mesh is not fine enough. A not fine enough mesh is characterized by a single point that has our maximum stress. So I'm trying to go fast because I only have 2 minutes left. So how do we change that? Well, we go here and we go to our sizing and we go to mesh and we go to our sizing and change size function. Oops, no. Relevant function, relevance, center, sorry. And we change that to fine. And then we go to our relevance and we increase that to 100. Now this increases the number of nodes and this changes the way that the computer thinks about it. The reasons that you wouldn't have maximum number of nodes is it takes longer to solve, it's less computationally efficient, etc. And you may simply not have enough nodes. Like I'm using the student edition here on my computer, which is limited to I think 50,000 elements. Which is, you know, enough, but it's not a heap. If you're modeling something big with a lot of forces in it, you'd probably want more. Alright, let's look at our thing. Right. Now, what can you tell me? Okay, so our regions of peak stress are now characterized by a line of stress through the material. Let's do a cross-section. Can I remember how to do a cross-section? I think it's that one. Yeah, that one. Rightio. Another thing that you need to know how to do, and I've got like 0 seconds to show you it, but we go down to statistics in our mesh. I'm going to ask you how to do this. Mesh metric, element quality, and then you need to be able to look at this element quality and go, oh yeah, are these good elements? And then your average is 0.77, which is pretty alright. It looks kind of funny in here. So a good element is one that's nice and symmetric and they're uniformly sized. Anyway, that's your shoot for today. See if you can get through that solid modeling stuff. And then next week, we are going to go through nonlinearity analysis. Cheers!